if you open your virtual machine or you manage to install the following instruction for Ubuntu, there is like the lab description that are present in the LocusInv robot control lab descriptions. And what I've printed for you now is the first lab description. This lab is about the joint space control, motion control strategies. In essence, the robot that we use is the UR5 robot. You can find in the same folder the description of the robot that has 6 joints. And this is the names of the links and of the joints. If you want to test the code, you just do in the locus in the robot control folder. You can check the joints and try to move the joints of the robot, launching Arbis, visualize.launch. So is test joints equal to true. To column equal to true. Of course, it's not working. So in essence, you should see the visualization of the robot, and you should be able to see some sliders that you can move, and you can see the motion of the joints. You understand why I tried before? Then this is a visualization, you will see the sliders. But if you launch the first lab, you can see a file called L1 fixed base joint space control. The one without anything is has the solutions inside, while the one without solution is the one you should work on and fill in the solution, trying to reply to the request of each question in the lab. So in essence, what this code does, if we quickly look into that, it uses the library of Pinocchio, that is a rigid body model library that computes the dynamics and the kinematics of the robot. The robot is called UR5 and has 6 degrees of freedom, and is a universal robot brand robot, fixed base robot. And so the idea is to compute the kinematics and dynamics through Pinocchio, and there is a ROS publisher that publishes the information of the joints to Arbis. That's why we are able to visualize them. And in this exercise, the dynamics it should be computed in the Python code, and we just send the joint position to the Arbis. So if we look after the initialization, we are getting the frame ID here, and setting the reference velocity, position, acceleration to the position to the default configuration. There is a config file called conf x1 conf pi. Wherever you have the delta t, that is the sampling time of your controller, you can change it, you can see whatever happens. And then you have the experiments duration, that is, let's say, the duration of the sinusoidal trajectory, while the total experimental duration is 5 seconds, wherever after the 3 seconds of sinusoids, the reference is set to a constant value. That's why we can see also discontinuity in the references. Slow factor, you can use it if you want to slow down the motion, to better see the motion of the robot. And here you have the P and D gains, proportional derivative gains. And here you can set the parameters for the reference, so for all the joints. So the amplitude, the frequency, and the phase shift. In this case, the phase shift is always 0, while the first exercise tells you to give 0.2 and 0.4 amplitude to the second and to the fifth joint, and with a frequency of 1 and 1.5 Hz. So you can see this is already preset here, while in the code, there is a while loop, and you need to write your reference for the joints here, and then you see exercise 2 is a step reference generation. Then after the reference computation, we have the Pinocchio that computes all the terms, mass, bias terms, colorless and centrifugal, and the gravity terms. So this will be included inside here, but we will use to do gravity compensation only. So the other exercise are the following, and then there is a possibility also to apply an external force. This is the last exercise, number 11. And after that computation, so we are able to compute the torque from the controllers and from the other external force. We give the torque we create a simple simulation by integrating the forward dynamics. So from the torque, we compute accelerations, and then we integrate with forward Euler integration. We don't care about better integrators here, just for simplicity. And then the data is logged into these variables, and the ROS publisher publishes the joint variables, and you have some plotting functions at the end. You can plot according, if you're giving position, velocity, acceleration, you can plot for all the joints the tracking in position, the tracking in velocity, and the tracking in acceleration. You can see how does it look like. This is the position one, the red is the result, and the Q is the actual trajectory. So yeah, now you can start to do the exercise. If you have any questions, just let me know. Exercise was to create a PD control law, and the result is that since you are not compensating gravity and the gains are pretty low, we see that there is a big steady state error, a big error even during the transient for the joints that are horizontal, so they are suffering gravity, which is the elbow, also the shoulder lift, this joint, so all the joints that are acting on the vertical plane, they have a superimposed tracking error. This joint is very lightweight, is the wrist one, and has no error. Also this joint that is rotating the shoulder pan in the vertical, with the vertical axis is not affected by gravity, and you see that the error is small. So how can we prove this? We can add a gravity compensation term, and you see that the error is reduced So the robot now it's able, before was entering even in the very below the floor level. Now it's more upright, and you see here that the tracking is still bad, but there is no steady state error at the end, especially whenever the reference is constant. So how can we improve the tracking? We can either increase the gains, go for the gains. I think you should go in the config file and increase 10 times the gains. So now we put rather than 50 and 20, we put 530. We don't increase too much the damping because with 1 millisecond sampling time, you can get instability if you increase the damping too much. So now we see the motion with the high gains, and we expect that the transient during the transient, the tracking it's a little bit better. Now we can try to. I will skip the critical damping one. In essence, if you set the reference, let's do that. So now we change the reference from a sinusoidal reference to a step reference. So the robot will just do a step, which is the second one. And you see that we expect some overshoot, right? Because we are not setting a critical damping. Actually, we should use the previous gains. So I will use the lower gains ones. The lower gains are okay. In this case, we have a little bit of overshoot here, for example. Here not, because the joint is very lightweight. But if we set the critical damping, so we set the KD gain to square root of the KP times the inertia of that joint. So we select the inertia of the joint, setting the one the diagonal. We neglect the coupling, so we are just taking the diagonal element of the mass matrix. Now we see that there is no overshoot anymore in that joint. This one this one are just the coupling, the inertial coupling that are there. So they are due to the motion of this joint and this joint. Actually, it would have cool to even two step in different moment to this joint and this joint to see, but you see that at least the critical damping behavior that there's no overshoot is nicely going to the reference. Then the next exercise is to improve go back to the sinusoidal reference and improve the tracking, giving a feed-forward term. So exercise 7, I give in essence the PD controller plus the gravity plus the mass matrix, the diagonal mass matrix times the QDD delta, that is the acceleration desired reference. And with that, we should see a little bit of improvement during the transient. Actually, good worse. So there should be a bug somewhere because the tracking got worse, or we need to understand why. Ideally, the QDD delta is just minus sign.
No, it works. I tried before.
You tried.
Yeah, it was working.
And now
Maybe you commented and commented.
Okay, so probably because we use the critical damping one. So it was improving.
Yeah.
Okay, that's strange. Okay. No, so these problems are related to the inertial effects actually. So it tries to improve. Actually, it's more prompt because we are giving acceleration, but still you have a lot of influence between these two joints. So the motion of one joint it's affecting the other joint. So if we do inverse dynamics, that removes the coupling effects, we should be able to achieve a perfect tracking. Yeah, so actually, yeah, I even was puzzled about even if I could give a feed-forward term, the tracking was bad, and it was due to the influence of the inertial coupling that were really screwing up the tracking of the two joints. Now, if we do inverse dynamics, ideally the tracking should be perfect, and it's not perfect here. Why? Do you know why?
It should depends on gain. KP and KE.
Yes, but we are linearizing the system perfectly. Why exactly at the beginning we are having some error?
Because the accelerations are computed 2 steps after.
No, but close. Because the initial, in the reference generation, no, we have a sign, then the velocity is a cosine, the derivative of a sine,
So there is a delay.
and it starts from, a cosine starts from 1. So to have 0, while our initial velocity, velocity in the simulation, it starts from 0. Right? So this starting from 0 creates a tracking error at the velocity level. And this is what shows up in that point. I think there is like no, somewhere I think I commented about this. No, maybe in the next lab. No. This one exercise 9. Let's try to see if we set a consistent value for the velocity.
Isn't it being over? Okay, no.
Sorry?
There's a spinning.
Yeah. And now you see that the tracking is perfect even in the beginning. Of course, whenever there is a discontinuity, then you lose the tracking because of discontinuity. Then I want to show you that if now the system is linearized, the tracking is good even if we reduce the gains. So let's put very small gains like 1/5 of the gains, and we will see that thanks to the inverse dynamics that linearize the system and the fact that there are no external disturbances, the tracking is still good. And you see that the tracking is still perfect apart from whenever there is this acceleration change. And then you see that the lower gain is taking more time to recover. And there is no inertial effect coupling in the other joint. This is very, very good tracking. What happens if I increase the gains a bit again, like to 320, and now I apply an external force. So at some point the external force should be applied after 2 seconds, I think. You see, tack. This is external force, 50 Newton up, and we should see here that even with inverse dynamics, we start to have tracking error. In this case, if we increase the gains, we will have, let's say we put 600, we will have half of the tracking error. So with external disturbance, the feedback gains, the inverse dynamics compensate for the dynamics of the manipulator, but not for the external forces. For the external forces, you still have the feedback part that should intervene to reduce.
So in theory we should have to measure the force and apply.
No, this is we don't measure the force. We just have a.
Yes, to fix this.
To fix this, we should be able to compensate for the force in the control action, and you will have zero tracking. Otherwise, you always have a tracking error.
Measuring.
Yeah, you can measure or estimate.
Or estimate from
Because it's not straightforward to measure. Maybe you don't have a sensor there.
I like this one.
Okay, that was, I think, the last exercise. So today we talk the lecture about we talk. Sorry, I lost a little bit. Operational space control. So we did what we will do. The next lecture will be a lab on operational space control and on the strategies. So the equivalent of this lab, but related to the strategies we presented in the lecture. And operational space control we implemented in 3 different ways: with inverse kinematics, with the Jacobian transpose from Whitney, Jacobian inverse from Whitney, and from which is called resolved motion control, and with the operational space inverse dynamics from Khatib, and then after this we were showing the orientation control problem that depends on different kind of representation of the orientation, and how to implement in the orientation control computation for each of these representation. So see you next week. If you have any question and feedback on the installations, let me know.
There's a course tomorrow, right?
Tomorrow.
Tomorrow. Sorry, tomorrow. Yes, no, not next week.